I'm going to start the recording. Welcome to the second lecture on GPU programming with OpenACC, which is sponsored by the National Supercomputing Mission and arranged by National Supercomputing Mission Nodal Center at IIT Madras. Yesterday, we looked at some basics of GPUs and more or less on the motivation behind parallel programming as well as GPU related aspects. Today we are going to develop our first code in OpenACC, which is essentially the hello world, and we'll look at some of the overall aspects related to the background of OpenACC. Tomorrow onwards, we are going to go deeper into the different constructs that are available. So let's start with the OpenACC basics. Right? So OpenACC is essentially an open accelerator language for C, C++, Fortran. And it was developed by a consortium of companies, Cray, NVIDIA, CAPS, and PGI, which was felt as a need in several years ago, almost 10 years ago, when there were more and more accelerators coming up, and people wanted to have some way of programming those beyond NVIDIA GPUs, right, for that matter. So people who had experience with OpenMP also came together and developed this pragma-based language for OpenACC for programming these accelerators. What does that pragma mean, etc.? If you have not heard of OpenMP and so on, that is all right. We are going to learn that in this course. One of the important challenges here was to meet and probably exceed the performance of handcrafted codes, right? Handcrafted parallel codes. So when I write some code, let's say using some library-based mechanisms like pthreads, the kind of performance that I might get might turn out to be different than what I might be able to achieve using a pragma-based language such as OpenMP on CPU, right? Similarly, on a GPU, the difference in performance might come in when I compare, let's say, handcrafted parallel code in OpenCL versus kind of pragma-based code, which is written with OpenACC. And that is kind of obvious. In general, you would, if you are given more control, you'll be able to probably parallelize much better. But that means that if you have more manually written code, then first of all, your productivity goes down. The expertise level needs to go up. I mean, there is a steep learning curve. Plus, there is possibility of creating bugs in your code, which are usually not so rampant in pragma-based languages or higher level languages. So therefore, with that motivation, that can we meet the performance? I mean, we will meet the productivity goal because you'll be able to write just a few pragmas and you should be able to parallelize your code. So that was all right, but then can we meet the performance aspects of the manually crafted codes? Right. So that was one of the main challenges. That gap is always going to be there, but as long as you are coming close to a manually written code with very fast creation of such a parallel code, I think that is really what people have been looking for. And when in cases where you require utmost performance, maybe that part of the code you can actually manually handcraft and add it to the code that was generated by a higher level language. But because of the performance related motivation or performance related challenge which is present in these pragma based codes, a lot of emphasis or responsibility is taken away from the programmer, but that doesn't mean that it goes away altogether. That responsibility is now given to the compiler. Now it becomes compiler's job to make sure that it actually generates high performing code. The second aspect which is important in the context of OpenACC and OpenMP is that portability. That I write the code once and I am able to run it on different kinds of, let's say, devices. Contrast it with CUDA, which I write, I spent months together in optimizing, creating and optimizing my code and correcting my code as well. And then once I have that code written, I can only run it on NVIDIA GPUs. right? I can't run it on other accelerators or other even machines. So we wanted some sort of a portability. Now portability cannot be given arbitrarily. That is, I mean, although the expectation is that it should run on a large set of accelerators, that needs to be provided. Somebody has to write a compiler corresponding to that. Somebody needs to support it for a newer device which might come up onto the into the market and so on. So that responsibility is there. But then can we still create some sort of a standard with respect to that these are the pragmas and this is the semantics of that pragma? That is, this is the syntax and this is the meaning. As long as we define this standard, so what this consortium has done is to create this standard. So OpenACC, although we call it as a language, it's actually a standard. Once you have created this standard, once you have created that, okay, this is how the specification should be, beyond that, then it becomes important to implement that standard in different compilers, right? So there are large number of different compilers which have been built to meet the standard that OpenACC has proposed, and different laboratories, different institutions keep coming up with more and more versions of OpenACC. So remember that OpenACC is a standard, similar to MPI. I mean, we say that MPI is a library, but MPI is actually a standard. It gets implemented in different libraries. Similarly, OpenACC. And therefore, the number of platforms that it can support is actually dependent on how much the community is spending time with it. So for example, we have this large number of different platforms like PowerPC and then Sunway, then x86, ARM, AMD, NVIDIA GPUs, etc. So all of these are supposed to be working, but that doesn't mean that you have the compiler directly ready for these. I mean, you can add your own hardware to it, but you'll have to also write the compiler corresponding to, and then the support will go on increasing. But the hope is that eventually people will start adopting it, and you'll be able to run it on a large variety of platforms. So take this portability as with a pinch of salt, that portability doesn't mean that you will be able to run it on any arbitrary platform. It means that you'll be able to run it on accelerators as long as somebody has created a compiler which adheres to the OpenACC standard. Okay. And with respect to this OpenACC, there has been a lot of revision since we said that it was started 10 years ago. You can see that there is large number of constructs as well as different features which have gone into different versions of OpenACC, right? So for example, let's say the latest version is 3.2, which has just come in 2 months ago. The earlier versions like 3.0, 2.0 and 1.0, these have come earlier, but you can also see the gap in performance, sorry, not performance, but a gap in coming up with these newer and newer versions, right? So for example, from 2013 to 2019, there was a gap, large gap when we were trying to come from 2.0 to 3.0. So there were a large number of features which had to be incorporated. There was a lot of discussion which had to be plugged in to make sure that we support all of these different features which are required by different companies, right? Not only companies, different users, I should say. Okay. So if you are installing OpenACC on your machine, you should be installing some 3.x version, right? So that most of these features that we are going to discuss are anyway supported in 2.x also. It's just that some of the compilers that you might have, the NVIDIA compilers, those may not work with the earlier versions, right? Because you will likely have a relatively new GPU. So install 3.x, right? So with that background of OpenACC, let's delve into our first Hello World program in OpenACC. Okay, so what am I going to do? I'm just going to write some simple piece of code, very similar looking to C, and I'm going to just try compiling it. What does this code do? It has hash include stdio.h, which is our usual standard input-output header, because I'm using printf. And then there is int main, which is the entry point for your C program. I have a brown colored hash pragma ACC parallel loop written in the slide. Of course, in your code, everything is black and white. So, and then there is a for loop which just prints hello world 0 to 9 times, right? That is 10 times I just print hello world in a loop, and I return 0 from main. What does this pragma mean? It just means that, boss, I want this for loop, which is just printing the values from 0 to 9, to be run in parallel by different threads on a GPU, right? So that is what I want to try out. Somebody might question that, well, I mean, you can write possibly printf 10 times in parallel, but I mean, that is not the best code to be parallelized. And that is true, that this may not be the code which you would like to parallelize. But since we are still working with hello world, we are allowed to write this 10 printfs in parallel. Right? So that is what you will do. Hash pragma essentially is a compiler directive in C, C++, Fortran. I mean, Fortran you will have bang dollar pragma, not bang dollar pragma, bang dollar, which is going to give some sort of a commenting, right, for the Fortran compiler. In case of C, C++, hash pragma is specially treated, which says that if I have some user driven or custom implementations or some sort of extra implementation beyond what the usual compiler wants, I can specify that as part of hash pragma. As an example, those of you who have done some OpenMP programming or have seen OpenMP programming, you would have hash pragma OMP parallel for, right? So that is going to say that there is some pragma which is going to be some construct, right? So some language constructs which are going to come after hash pragma, which may not be understandable by your usual compiler, but might be offloaded to a different compiler so that that compiler will make sense of those constructs. In case of OpenMP, it is going to be OpenMP compiler, which is anyway going to be part of GCC. Maybe some library is going to come into picture there. In a similar manner, in case of OpenACC, there is going to be an OpenACC compiler, which is going to make sense of this particular construct. And it doesn't stop there. The reason being that although I'm specifying it just as one line, that compiler has to transform your code. That compiler needs to transform your code, which you have written already, to make sure that certain things happen in a different way, right? So in this specific case, we would like this for loop to be run on the GPU first of all. If I don't have this pragma, then the CPU is just going to print this hello world 0 to 9, right? But I want this to be offloaded to the GPU. That is one. Second thing is I want this to be running parallel, right? So these were the two changes which we are suggesting the OpenACC compiler to do. And let's see if it is able to do that. Okay. So the way I'm going to compile it is not using GCC, but I'm going to compile it with a different compiler called as PGCC, which comes when you install this NVIDIA HPC toolkit. So let's say that that is in the path, and I'm going to store this file as hello.c, and I'm going to say pgcc hello.c. Very similar to what we compiled with gcc filename.c, right? So your file name need not be OpenACC or something. You can just have .c as the file, and that compiles. And if the compilation is successful, then I get a default file a.out, which I can run or which I can execute, and I get the output hello world 0 to 9 exactly the way I was expecting it to be. Okay. Any questions so far on this basic hello world program? All right. So if there are no questions, I'll move ahead from here. One of the things that I would like to do is to change this number 0 to 9, I mean this loop count as 10 to 100. What I do is that I just change it to 100 and I just compile it again with PGCC and I run it. And I get the output as 0, 1, 2 all the way up to 99. Right? So that is expected again. Does anybody see any issues with this output? And as we discussed yesterday, Please feel free to interrupt anytime. You can discuss questions anytime. Let it be interactive. It's perfectly fine. Okay, so the question here is, I get this output 0 to 99 in the same order, very similar to the CPU output. Does that bother you or it seems okay? Prasun is saying order can be interchanged, right? Okay. Swapnil says possible order may not be the same. Okay. Any other suggestions? So what I do is that I run this a few times, right? You are right. So Prasun and Swapnil, what they are suggesting is that if you are running this in parallel, I mean, it's not guaranteed that you will get exactly the same output as a sequential CPU code, right? 0 to 99, right? You might, some interchanging might happen. Maybe you will see Hello World 5 written first instead of Hello World 0, right? That should be possible. Maybe if one time I was lucky or strange things happened, and therefore let me run this code a few times. And when I run it a few times also, somehow I still get the same output, 0 to 99. That should ring a bell in your mind that maybe that means that things are going sequentially. Things are not running in parallel. This code is probably not doing things in parallel as I was hoping it to be. And this is one of the interesting parts about OpenACC, that you might see the same output, but you might not realize that whether you are running the code sequentially or in parallel until you profile the code and see that there is timing difference and so on. So you have to be careful in this aspect, and that's one of the reasons why I have highlighted this part, that you will get the output 0 to 99. That does mean that it is not running in parallel, it actually is running sequentially. And that too not on the GPU, but it is running on the CPU. Okay, and why is that? That happens because I need to specify some command line parameter to tell PGCC compiler that boss, generate code for a GPU and run it in parallel. Don't generate code for a default device, maybe it is CPU. Right? So this shows you that you are probably, so with -acc as a command line argument, you have to compile it again, and then when I try to run it, then I get some output like 96, 97, somewhere interspersed, then 0, 1, something. And this output also changes when I run it multiple number of times, right? So then it made sense that the output is actually running in the program is actually running in parallel, and therefore you should get orders differently across different executions of this simple hello world program. Okay. All right. So just a brief note on the OpenACC installation and its compilation as well as use, that you have to install this NVIDIA HPC SDK on your machine. You could have a Linux or a Windows based implementation from this HPC SDK website from nvidia.com. And the installation instructions are also given in the same Google Sheet that I have shared. If you want to use C programs, that is whatever we were looking at, you can use PGCC. For C++, there is PGC++. For Fortran, there is PG Fortran. Most of the constructs that we are going to look at, those are all going to be demonstrated in the context of C. But all those constructs, I mean the OpenACC constructs, are anyway going to be available in the context of Fortran also. At one place, there is a small difference between the C and Fortran meanings. So that I'll highlight, but otherwise most of the constructs are the same. Right? And if you face any issues with respect to installation and usage of these, if you face any problems, feel free to post it on our Google group. Either me or Josh will take a look at it. But if you are not able to solve, maybe some of the participants may have faced those issues, and if they have solved, they'll also be able to help you. Okay. Yeah, Tony is asking, is OpenACC supported for AMD graphics cards? I don't think so. Currently, I mean, yes, it is supported, by the way. Okay, it is supported, but not this particular compiler. I think there is some other compiler which you will have to install, but as far as this NVIDIA SDK is concerned, that is going to work only with the NVIDIA GPUs. We'll have to find out if there is a different OpenACC compiler which is supported for AMD graphics cards, which I'm not aware of, but hopefully it should exist somewhere in AMD. Maybe some HPC part is available. Okay, Swapnil has given that tool available. Thanks, Swapnil. Right, so this is what helps in posting your questions on the Google group or even in the chat, that if students have faced or other participants have faced similar, I mean, they might know some of these aspects already. Good. All right. So yeah, there was another thing from our yesterday's discussion which I wanted to quickly highlight, that somebody was mentioning that we have reached the exa scale, but that didn't seem to be the case from our top 500. Anyway, we'll come to that when we reach there. Okay, so this seems fine. One small check which you might want to do after successful installation of OpenACC is to run this command called pgaccel-info. Right, so this PG comes from that PGI. We said that there is a PGI group which is also part of the consortium which developed OpenACC standard. So that PG comes from there, and accel-info is essentially the accelerator information, which can give you some information about your installation as well as the GPU associated with your machine. Right? So you might get some output, something like this, where you specify some sort of a driver version, then the kernel module of your NVIDIA driver, then the device on which you are going to run, that is the GPU number. If you have multiple GPUs, these are usually numbered as 0, 1, 2. Then the device name, for example, here Tesla is a family of processors or a type of GPUs which are created, Tesla, Fermi, these are different types. And then V100 is our Volta 100, which uses the PCI Express bus for the interconnect between CPU and GPU and has 16 GB of RAM. Then the device revision number, which is similar to your compute capability, right, that we were discussing yesterday, which is for 7.0 for Volta. Global memory size is 16 GB. Number of multiprocessors, which is essentially the component which runs your multiple threads, right, in parallel. So one SM or one multiprocessor is going to have multiple cores associated with them, and all of those are going to run in parallel, and there are multiple such multiprocessors available. For example, in case of Volta, as we saw yesterday, we had around 5,000 something number of cores which are spread across these 80 multiprocessors. Right? Concurrent copy and execution, which means that you can, while you are executing some code on the GPU, you can transfer data between CPU and GPU. Right? So that is concurrent copy and execution on the GPU. Right? So that was not supported earlier, but most of the recent GPUs do support that. Constant amount of memory. Constant memory is a memory which can be used as a fast read-only memory on the GPU, whose size is little limited, 64K, but it can be very useful if you have some sort of metadata information which is not changing across the execution, which you can then push into the constant memory, and it has faster access than directly accessing RAM, which is a read-write. Similarly, there is something called as shared memory per block. This block means a thread block, which we are going to study. In our OpenACC context, this is called as a gang. Right? So this is shared memory per gang, which is typically 48 KB, which is again something which you can program at the CUDA level or OpenCL level, but may not be possible to be done with our OpenACC constructs that we are going to study. Similarly, there are certain number of registers, 64K registers available per block. Then there is something called as a warp size, which is about single instruction multiple data format, which we are going to call as a worker in our context. And I'll explain that in a little while. And the number of threads per block has a limit, 1024. So okay, these numbers you don't have to by heart and don't have to worry too much about it. What I'm going to, I mean, as a summary, what I would say is that since you are able to run large number of threads on a GPU, these need to be organized. You cannot just have a flat um, organization where each thread is independent, right? So all of these need to be organized. So one thread is one execution unit, software unit. Multiple such threads are going to be pushed together into something called as a warp, which all execute the same instruction, maybe operating on different data items. So SIMD execution is going to come for that warp. Multiple such warps form a thread block or a gang. Multiple such thread blocks are assigned to a multiprocessor, which is also called as a SM, streaming multiprocessor, and multiple such streaming multiprocessors are available inside a GPU. I'll show this pictorially also as we go along, but just wanted to highlight that. So the bottom line here is that if your installation of OpenACC is successful, then PG Axel Info should show you some of this information properly. Okay. Nitin is saying that you mentioned yesterday that there are some libraries or plugins kind of software that allow us to convert our Python ML code into OpenACC CUDA, etc. My question is, say there is some high level abstraction provided in Python that aren't supported in OpenACC or CUDA. Is in that case, what should be the recourse action that we need to take? So if it is not supported directly, then we have to run that part in sequential, either on CPU or even on GPU. For example, you can run things directly on the GPU also sequentially. So if you don't want to do data transfer here between CPU and GPU, you can actually run it on the GPU sequentially. Alternatively, you can run that directly on the CPU, and most probably it will be running sequentially on the CPU. Okay. Any other concerns, questions here? All right. So I'll move ahead from here. So some of the OpenACC syntax, we saw just one type of syntax, right? Hash, pragma, ACC, parallel loop. Right? So there are the types of such statements is little large in number, but the ones that I mean, we can cast those in a particular format. So all of those are, in case of C++, are of type hash pragma ACC, followed by certain directive like parallel, and then there are certain clauses available. Those clauses help you control the execution in a more fine-grained manner. Think about those clauses as parameters which can change the behavior of the underlying parallel computation. Right? In this case, I mean, I can say that loop is coming as a clause, but loop is also a directive. For example, you can have hash pragma ACC parallel and hash pragma ACC loop. That is also, so these both are essentially directives, but you can have more specifications which specify, for example, certain data may not be present on a GPU, so maybe you should copy it, or maybe you should copy it only if required. Maybe you should allocate that memory, or maybe there is a different kind of processing which I should be doing when I'm executing this particular loop in parallel. Right? So all of these can be specified as different clauses. Maybe there is, if certain condition is specified, then only make it parallel, and so on. So all of these can be specified in the clauses. The Fortran syntax is very similar, and from what I know, there is at least one person in our group who is working with Fortran. So I'll specify that here. Bang $ACC is going to, I mean, bang specifies a comment in Fortran, but there is a special type of comments, very similar to our Java doc comments, right? So we have this /* and then /**, and beyond that you can specify @author and so on. So all of these are very specialized comments which allow you to still compile the program, right? Even if you don't have support for OpenACC. So you specify the directive and the clauses, and that turns out to be useful in Fortran also. So one of the ways in which these pragmas help is that you write your sequential code without any pragmas. Right? You write your completely sequential code, make sure that it is correct and it is reasonably okay with respect to all the optimizations that you wanted to make and so on. Once you have done that, identify which part of the code is most time consuming. How will you identify that? Well, you actually run the sequential code and time different parts of the code. Typically, the for loops or the recursive functions are going to be the ones which are going to take the maximum amount of time. Identify those loops, choose one of them and add a pragma. Hash pragma ACC parallel for or parallel loop or hash pragma ACC parallel, whatever you want to add. Or in case of OpenMP, hash pragma OMP parallel for. Just before that loop, and compile and run the program. Of course, compilation will have to specify some flag, like in this case we specified -ACC. There you might specify -F OpenMP and so on. Once you have compiled this program, you try to run it and check if you are getting any performance benefit. Right? Maybe you are getting some performance benefit, but not as much as you expected because you have parallelized only one loop. But assuming that you have parallelized it correctly, check if the output is turning out to be the same as the sequential output. If that is the case, then you can go for the second loop to be parallelized and so on. So what this pragma based languages allow you to do is to do some sort of incremental parallelization. You start from a sequential code and go on parallelizing it step by step and finally have a completely parallel code working at every stage. Right? That is, the correctness is guaranteed at every stage because you are manually checking it after every stage. So that is very nice. Contrast it with what happens in a totally new language where I have to specify, I have a sequential code which is running in one language and now I am developing a parallel code in a different language because the new language is specific for parallelization purposes. So I have to rewrite the whole code. Right? And I cannot incrementally go on developing it because the code, it needs to be developed completely, then only I'll be able to compile and run it. Of course, you can do some stuff that, okay, I don't compute everything and so on. But the advantage that you get with pragma based languages like OpenMP and OpenACC is that you can incrementally develop, and that can be a very, very important advantage because as we discussed yesterday, the domain expert might not be the HPC expert. So that person may not have all the expertise to parallelize the whole program suddenly, right? But if you go part by part, that will be helpful. All right. So Prasun says that he also works with Fortran. Good. So I'm sure you will find some of these parts helpful. So that is what was the incremental parallel development that I was talking about, which is very helpful for pragma-based languages, which is not possible or it has limited applicability in the context of other parallel languages. Other thing is it is portable. As long as you have a compiler for it, you just have this particular syntax and it will run. In case it doesn't run, by the way, in case it doesn't run, in case some construct is not supported on a particular device, you can always resort to the sequentiality. And that is a big plus when it comes to pragma-based languages like this. Additionally, it's a single source, right? So the same source, I don't have to rewrite the code. Maybe if I have to write CUDA code, that will work only for NVIDIA GPUs. If I have to write for, let's say, AMD, maybe I'll have to specify, use a different language and recreate the code. Maybe if there is some other Xilinx FPGA, maybe I will have to write it in a different way and so on. But the advantage of OpenACC is that you write the code once, and as long as you have compiler for it, you will be able to generate code for different devices, right? And I'll show you an example of this, again using Fortran as an anecdote. If I have some hello world program or some Fortran program written in this hello.f90 file, and I compile this program with PG Fortran, I'll develop a sequential code. I'll create a sequential code which is going to run sequentially on the CPU. If I add -TA equal to multicore, that particular code will start running in parallel on the CPU. If I specify -TA equal to Tesla or -ACC, that is going to generate parallel code from the same source code in hello.f90 to be running on the GPU. Right? So this is a very beautiful, advantageous way, a very productive way of generating codes for different backends using the same source code. Right? So that is what is the holy grail, that I write my code and that just works across multiple devices. Of course, the actual holy grail is that I write sequential code and the compiler takes care of generating parallel code for different devices and so on. Right? That is the real holy grail, and we are far away from it. All right. If there are no questions, I'll move ahead from here. So that way, those of you who have some experience with CUDA or OpenCL or even pthreads for that matter, you'll find that using OpenACC or OpenMP is going to be relatively much easier. Those of you who have OpenMP background, you'll actually find a lot of similarity, and you'll also appreciate that it is very similar to OpenMP in terms of the expressivity as well as the ease of use. Those of you who don't know anything about parallel programming yet, you'll find that OpenACC is reasonable and you'll be able to learn it quickly and also generate nicely parallel codes towards the end of this course. One of the mantras that this consortium had was that we should do more science and less programming, right? And that's also something to do with what the other languages provide, like CUDA and OpenCL, where we have to actually write a lot of code to get one small piece of code parallelized. Right? There is a lot of boilerplate code that we have to write in OpenCL for that matter, which can also be time consuming as well as error prone. But here it's going to be much simpler. Right? So we should focus more on the domain part of it rather than the HPC part of it. Let the HPC part be taken care of by the compiler. That is the goal. Okay. One of the homework exercises for you is to, that doesn't mean that we have come to the end of the class. This is only for this particular slide, that you have to read the output of PGCC or PGC++ or PG-Fortran-help, and you will realize large amount of different functionalities that are provided in your compiler. Of course, some of the main ones we are going to make use of and study in this course, but there are lots of different clauses which are supported in these languages, which need to be learned over a period of time rather than a 2-week course. Okay, so recall this diagram. I'm just going to show you how OpenACC is going to make use of this diagram. But the idea here was that the CPU reads data, transfers some data to the, offloads some computation to the GPU. GPU executes the kernels or some parallel computation, gets the results, transfers the host or the CPU gets the results back from GPU and then makes use of those on the CPU again. Right? So this was our overall CPU-GPU computation, and OpenACC execution model is essentially adhering to this particular view. Okay, what does that mean? That means that the overall computation is driven from the CPU. Therefore, it is also called as a host-directed execution model or host-directed computation. That means that the CPU is the main driver and the GPU is used as a coprocessor, right, or an accelerator, which is going to make use of the additional processing which needs to be done. It could be a GPU, it could be an FPGA, whatever, some parallel device. So what are the different tasks that the CPU initiates? What are the tasks that CPU needs to initiate? Well, it needs to allocate memory on the accelerator, right? This memory is getting allocated on the GPU, but it's not the GPU who is doing it or initiating it. It's the CPU who is initiating this. Initiation of the data transfer between CPU and GPU, whether it is from CPU to GPU or GPU to CPU, that also needs to be initiated by the host or the CPU. Then sending the code to the GPU driver, right? So code meaning the actual executable part, the binary code which needs to be running on the GPU, that is present in your a.out file. Right? So that needs to be that gets copied in the CPU memory, the CPU functions. But whatever is the GPU part, that needs to be executed on the GPU. So that needs to be transferred to the GPU. It doesn't happen that when you compile your program with PGCC, then whatever is the CPU specific part that sits on the disk, and whatever is the GPU specific part that goes into GPU memory. That doesn't happen. Everything is there in that A dot out only. The CPU part gets loaded in CPU memory. The GPU part needs to be transferred to the GPU memory so that the GPU execution engine can run these kernels on the GPU. Similarly, when we have these execution, all these functions, parallel functions running on the GPU, those also need to be passed certain parameters, right, which will be given to different threads, and then they can operate on these arguments. For example, I might want to pass a vector or address to an array as an argument to all the threads so that they can operate on A of I in parallel. Okay. This also is done by the CPU. Right? Then queuing of the accelerator code, which means that whenever I am trying to invoke certain function or a kernel on the GPU, this particular code gets queued up into some sort of let's say FIFO buffer, and at some point in time, the NVIDIA, or in this case the device, there is a driver associated, it pulls up different or extracts or dequeues these codes from the, it's not a code, it's just a pointer, that these functions need to be executed on the GPU. Some of these functions could be kernels, but some of these functions could be the data transfer instructions, right, which is happening between CPU and GPU. While this is happening on the GPU, while some function is executing in parallel on GPU threads, CPU can decide to wait for completion of that and get the results back to the GPU, back to the CPU, and then also deallocate memory, that is at least initiate the deallocation of the memory from the CPU side. So as you can see, most of the part is getting done by the host. The actual execution of the kernel functions, actual execution, parallel execution on the GPU threads is only happening on the GPU. Of course, GPU is involved in many of these parts, because when you are allocating memory on the accelerator, that is on the GPU, GPU has to be involved, right? So there is a driver piece which is going to be part of the GPU, which is going to be running, which needs to be communicated with from the host side driver part of, in this case, NVIDIA GPU. So all of this does require a handshake between the two CPU and GPU devices, but it all gets initiated by the host, and therefore this is called as a host directed execution. There is a question. Himanshu says, why should we prefer OpenACC over OpenMP? OpenMP currently does not have full support for all the accelerators, right? So that is still in progress. OpenMP 4.0 onwards, we have support for accelerators, specifically for GPU. So that is still coming up. Currently, what I see with respect to my experience with OpenMP on GPU and OpenACC on GPU is that OpenACC is much ahead. Not only in terms of the flexibilities that it provides or the functionalities that it provides, but also with respect to the optimized code. Okay, I have seen that OpenACC compiler is actually very well written, and you will get, if you are careful in writing the code and not messing it up, OpenACC can give you a very, very optimized code. Right? And I'm very happy with the OpenACC compiler as far as my experience, my personal experience goes. OpenMP will catch up. I think it will take some time. Maybe eventually, this is my guess, but maybe eventually you might have only OpenMP, which will work across all devices. That is possible. But as of today, OpenACC is definitely doing very well. Josh has given some reply. OpenMP is mainly used for parallelization on the multi-core CPUs. However, OpenACC can be used for parallelization on CPU as well as GPU. Yes, that is there. Yeah, using OpenACC, you can generate code for CPU also. Right? So that is definitely in as of today. So you should be able to make use of OpenACC compiler anyway. And my suggestion is try it out. Just run your code with OpenMP pragmas as well as OpenACC pragmas on the same input, and see what is the performance you get on CPU. My feeling is that you will mostly get similar performance on the CPU, but then try running it on the GPU and you will see much bigger difference between them. Good. So I'll move ahead from here. So that was the first part, that it's the host directed execution model. And whatever is compute intensive part, whatever is large amount of number crunching, data parallel operations, all that part can be offloaded to the GPU. Right? So make use of the GPU more like uh, let's say an assistant. Right? So that is what is the overall OpenACC execution model. Which what this means is that the standard actually thinks about these two devices in an asymmetric fashion. It doesn't view all these devices same, right? So that's the main point that I want to bring out here, right? So whatever are the parallel regions in your code, that can be offloaded to the GPU. Then there is something called as a kernel. So this parallel region is hash pragma ACC parallel. So that can be offloaded. The kernel is hash pragma ACC kernels, which you can specify. This is one of the beautiful constructs in OpenACC, which can be actually very useful when you are starting your OpenACC programming. So what you do is that even before you profile your code, what you can do is that, okay, this is my sequential program, right, which is working correctly. The first instruction in that, I'm just going to specify hash pragma ACC kernels, right? And then maybe opening brace, and then that brace closes towards the end of main. What does this mean? That, okay, I have specified that this particular computation is amenable for GPU parallelization. Go figure out which part should be run on the CPU sequentially and which part should be run on GPU in parallel or sequentially. Right? So if you find some loops in between, automatically try converting those to GPU. If you find that there is some sequential code, maybe try running it on the CPU itself. Maybe sometimes you feel that there is a lot of data transfer happening. Go figure out if you want to execute that on GPU, etc. Right? So it's almost like the compiler is given full control of your code, and the compiler will try to figure out all the dependencies, where loops are, etc. And it will just try its best to give you some parallelized code. Right? This construct actually, in that sense, is what we look for eventually. That is the final holy grail that we are expecting. That I take a sequential code and somebody just compiles it and gives me the parallel code. Right. So if you are interested in parallelizing your first code, you might want to try this pragma kernels pragma, right, which we are going to study 2 days from now. All right, and the other one is actually execute serial regions also on the GPU, as I was mentioning. Sometimes the code might not be parallel. Sometimes there might be just assignment to one global variable or one variable which is shared across all the threads on the GPU. You don't want to run that in parallel, right? So in such cases, the compiler can decide, or you can decide, that some code I would like to run on the GPU itself, but sequentially. Shri is saying, can OpenACC be used for multi-core microcontroller like STM, which has ARM Cortex M4 and M7? I don't know if that support is there yet. Yeah, Josh is saying that it depends upon the PCC compiler. If there is a compiler for it, then yes. Yeah, I'm not sure if it is, that support is currently available. Right, so yeah, so ARM has its own GPU, but yeah, I'm not very sure if that support is there. Somebody will have to look it up. Unlikely that it is available. Yeah, that is my guess, that unlikely it is going to be available. All right, so we'll move ahead from here. Any questions on this OpenACC execution model? I'm going to say a few more things about the execution model, especially about the how the offloading happens. And I was talking about that buffer, command buffer. So how does that happen? So one important piece that we should understand is this, that the CPU can run asynchronously with the GPU. That is, the host can run asynchronously with the device. What does that mean? That means that I can say that, okay, go execute this code on the GPU, and I don't wait for that execution to finish. I meaning CPU. And CPU can go ahead and execute the next instruction. This is one of the very complicated, interesting as well as complicated things which the OpenACC execution model can do. The reason being that it can change your sequential output. In the sense that when I run the code sequentially, I get certain output, but when I add these pragmas and execute certain parts on the GPU, I might get a totally different output and sometimes unexpected, which can be actually wrong. So therefore, we should be aware of this asynchronous execution, and many times we expect that the execution should be synchronized with respect to the GPU execution, which means that when you are running something on the GPU, the CPU should wait for that execution to finish, because that's what happens, right? So you have a for loop, and then there is some statement after the for loop. That statement is going to get executed only after the whole for loop is over, only when the last execution, last iteration of that for loop happens. It doesn't happen that suddenly that statement gets printed in between while the iterations are still executing. Right? That doesn't happen. But that can happen because of this asynchronous execution, and we'll look at some of the codes which can trigger this asynchronous execution. Okay. So we'll study that in our next class. Yeah, so this was what I was talking about, that there is a queue of operations which gets maintained, which is related to the accelerator or the device, which is called as device activity queue. Into that activity queue, different operations get inserted. Right? So for example, I'm showing a few queues here between CPU and GPU. The driver from CPU inserts the next operation into a queue, and the driver from the GPU can extract different operations from the queue. When we are dealing with a particular queue, all these operations must be executed sequentially. When we are dealing with one single queue, that is one horizontal gray colored queue I am showing, that all the operations within those are executed sequentially by the GPU. That means that until the first, let's say I am launching 3 operations in the first queue, right? K1, K2, K3. These are 3 kernels. K1 itself can run in parallel, but until it is over, K2 will not be taken for execution. And until K2 is over, K3 will not be taken for execution, and so on. So individually, these are running in parallel. That is K1, K2, K3 individually are executed with multiple threads, but K1 has to finish before K2 begins, and K2 has to finish before K3 begins. However, across these multiple queues, you can still have parallelism. That means the GPU can execute K1 from one queue and maybe K100 from some other queue, and both of these might be running in parallel on the GPU. Some of you might have misheard that a GPU is capable of running only one code at a time. That is not the case. In fact, the reason why you have heard that is also valid, that earlier GPUs used to have a single kernel running at any point in time. But these days, all the GPUs are capable of running multiple kernels simultaneously. And therefore, you will be able to have, that is coming because of these multiple queues. In the context of CUDA, these are called as streams. So if you have multiple, all these new GPUs have stream support. So those of you who have probably misheard this, please remove that misconception from your mind. The host thread, that is the CPU driver, which is invoking all these operations, it can query and wait for the queue to get over. That means that it can wait for certain operations and it can check if a certain functionality has been over. Maybe a certain kernel is finished or not. And multiple queues can be simultaneously active, which allows multiple kernels to be executed on the GPU. As far as the GPU execution is concerned, in OpenACC, the accelerator has 3 different levels of execution or parallelism. That is what we were talking about, but let me specify that clearly here. The first one is the gang. which is a very coarse-grained, high-level grouping of threads. Right? This is also called as a thread block in the context of CUDA. The second one, which is more fine-grained, is called as a worker, which is essentially is going to run on a multiprocessor. So this worker is also called as a warp in the context of CUDA. And then at the lowest level is, well, it's not really a lowest level, but it's called as a vector in the context of OpenACC, which is the single instruction multiple data format, which on the CPU will use some sort of vector instructions. Right? But note that this is not really the final. There is something called as a vector lane, which actually is running a single thread of execution. Right? So there are essentially 4 levels, so to say, but the OpenACC standard specifies only these 3 from the perspective of the programmer. The reason why these need to be specified is because you can control these. You can control what is going to be the gang size, how many threads you want inside the gang, or how many threads you want inside a worker. So all of this is manipulatable, programmable. So you will be, we'll study some of that in our examples. Yeah. Okay, if there are no questions, I'll move ahead from here. Yeah, so this is the hierarchy that I was talking about, and it has come at the right place where we are discussing about this thread and vector lane. So at the lowest level in this hierarchy is a thread, which is the actual execution of a code. If I have a for loop, one iteration typically is what one thread will execute. Or if I have a function which I'm parallelizing, then one instance of that function is going to be executed sequentially by one thread. Right? So that is called as a vector lane. Multiple such threads together in are grouped in a warp, which is also called as a worker. This particular warp actually should be executing in a single instruction multiple data format. That means that all the threads in this warp execute exactly the same instruction, or I mean, there are ways in which you can make only a few threads execute certain instruction. At that time, the other threads will be executing, will be masked out. That is, they will not be executing any instruction. So that is a warp level. Multiple such warps, and typical size of a warp is 32 in NVIDIA GPUs. Multiple such warps together form a thread block or a gang, which are simultaneously assigned to one particular multiprocessor. Right? So one gang, I mean, although the OpenACC model doesn't say so, but one thread block, when it gets mapped to a thread block in the context of GPUs, NVIDIA GPUs, I should mention that one thread block does not move from one streaming multiprocessor to another. There are multiple streaming multiprocessors available, but each multiprocessor gets a few blocks together or a few gangs, and a block does not move from one multiprocessor to another. So if it is in contrast, think about thread on a CPU. If a thread is executing on one core, it is possible that after some time that thread might be executing on another core. Right? That doesn't happen in the context of block to multiprocessor mapping. That is fixed. Okay. And multiple such multiprocessors essentially form the overall GPU, or the accelerator that we are talking about in this context, which is capable of running hundreds of thousands of threads in a time multiplex manner. And as we discussed in the context of Volta 100, we have a few thousands of cores available on the GPU. So a few thousands of threads can actually simultaneously run on the GPU. Beyond that, it's going to be in a time multiplexed manner. Right? So although you are allowed to launch a kernel on the GPU with even millions of threads, but only few of them will be active at any point in time, depending upon your hardware constraints. Dubajyoti is asking, so a GPU advertised with n number of CUDA cores, which level are we talking about here? Vector lane? No. When a GPU is advertised with n number of CUDA cores, that is actually across all these multiprocessors. right? So when we say that there are 80 multiprocessors and each multiprocessor might have, let's say, 56 cores, then that is the hardware part. The block, warp, and thread are actually coming more from the software perspective. But yes, you are right that a thread is actually associated with a core, and therefore we can say that those many vector lanes are simultaneously going to be active at any point in time. So you can, at a indirect level, you can think about vector lanes in that way, the number of cores, but actually a single core might actually be running multiple vector lanes at different points in time. So that's, I think if you remember this, that block, warp, and thread are software concepts, whereas multiprocessor and GPU as well as the core are the hardware concepts, then I think things will be easier for you. Himanshu is asking, all threads in a gang execute the same instruction? No. All threads in the gang can execute different instructions. In fact, different warps can execute different instructions at the same time. It applies only to the warp as far as the same instruction execution goes. Yeah, Tony. Tony, go ahead. Or
yes. In the context of this picture, how does this streams come into picture?
Okay, so a stream is associated with a kernel. So, okay, I shouldn't say kernel, but a stream is associated with a particular GPU. In fact, multiple streams are possible to be connected with a GPU. And from the CPU side, we can insert multiple operations into these streams. So when I say that I'm launching kernel 1 into stream 1, the CPU will insert kernel 1 into this stream and the GPU will take it for execution at some point in time. And it will use its multiprocessors in some arbitrary manner to execute that particular kernel 1. At the same time, CPU says that, okay, in stream 2, which is also associated with the same GPU, invoke kernel 2. That kernel 2, assuming that the GPU has free space, will start taking out the kernel 2 for execution at the same time, and kernel 1 and kernel 2 will possibly be running at the same time on the same GPU. There is a good chance that it will use separate multiprocessors for the two kernels, or it will use them in time multiplexed manner, right? So both of these are possible. In fact, some of the newest GPUs which are supporting this virtual memory concept, they'll be able to even swap out one kernel and swap in another kernel for execution, right? So that is also going to be possible with some of the latest GPUs. So stream is associated with a GPU with respect to different commands that we can execute on the GPU. Those commands will make use of all these multiprocessors and blocks to execute. Those commands need not always be related to kernel execution. Even the memory copy operations can be assigned into this stream.
Right. So essentially, multiple streams can be mapping to same GPU card or multiple GPU cards. Both are possible.
Both are possible. Right. In fact, one stream is going to be associated with only one GPU.
Right. Thank you.
Okay, no problem. So Sivro has a question. So the GPU driver automatically decides the number of threads that has to be run, like the OS for a CPU, or it has to be specified by user by some settings. If we don't specify, then the OpenACC compiler, not the driver, the OpenACC compiler is going to decide, OpenACC runtime is going to decide how many threads with which it has to launch the kernel. But as a programmer, I do have the capability to change that parameter. So we'll be able to specify the number of gangs, number of workers, and that should be possible to be changed. If you don't specify, then some default value is going to get used. Tony is saying one multiprocessor can execute one function. This part I am not sure. Most probably no, but I'm not sure. My guess is that the multiprocessor can execute multiple functions in a time multiplex manner. But yeah, I'm not very sure about this. This is what I guess from, because we are allowed to run multiple kernels simultaneously on the GPU. So this is definitely one execution model where I take one kernel, execute it, and then execute another kernel. But since simultaneous execution is possible on the newest GPUs, I would imagine that at the multiprocessor level, multiple executions of the kernel is also possible. Justice saying one string multiplexer can execute multiple kernels in time multiplex manner. Sure. Thanks, Josh. All right. If there are no further questions, I'll move ahead. Yeah, so this was what we were discussing yesterday, and this is where I wanted to just clarify that we have, at least when I looked up today, I think the maximum performance we have achieved seems to be 0.5 exaflop, and I don't think we have crossed that barrier. But in case there is something which I'm missing, please let me know. So top500.org is a listing of the most powerful machines, essentially called supercomputers in the world, and 500 such supercomputers are listed. And you guys have already told which one is the fastest supercomputer yesterday, you had told. So this list gets updated every 6 months, June and November. And as you guys have mentioned, flops is the one that gets used, which we discussed yesterday, floating point operations per second. And as of 2 months ago, 3 months ago, the Fugaku supercomputer, which has over 7.6 million cores, is rank 1. Does anybody recall what is rank 2 without actually going to top500.org? Or at least which country it is from? Okay, Suro says US Department of Electronics. Himanshu says US. Dhruvajyoti says Summit. Okay, all of you seem to be pointing to the same one. Yes, it is Summit from US, which is at rank 2. And then there are 3 more which I'm going to list here, but there is a long list on this. So there is Sierra from, again, US, and then Taihu Light from China, which at some point in time was the first one. And then there is Pearl Butter, which is again from US, which has just close to 1 million cores, right? So you can also see the number of cores that get used and how their utilization is. For example, Taihu Light has 10.6 million cores, but it is at rank 4, whereas Sierra has only 1.5 million cores and it is at rank 3. Right? So how you utilize the cores is also important. What is the algorithm, the hardware improvements that have gone into the core, that also starts mattering, and so on. Okay, this is more for your own just background study, but one question that I have is, one homework exercise for you is to check out what is India's rank there. I think somebody had mentioned this yesterday, and where this computer is, and approximately how many cores does it have. If somebody knows quickly, please feel free to answer. Otherwise, take it as a homework exercise. Okay, Himanshu says Param Siddhi. Good. And where is it? Okay, so maybe you can think about it. It should be in CDAC. There used to be another supercomputer earlier, which was top one from India, whose name was Pratyush. That was in the other IITM, right? When I say IITM, that doesn't mean IIT Madras. The other IITM means is the Tropical Meteorology Department from Pune, where that Pratyush supercomputer was. All right, so I think this will be an interesting thing to look at. The important compute constructs that we are going to study as part of this course are hash pragma ICC parallel, which is going to allow us to parallelize not only loops, but even other execution statements that you might have in your program. Right? Although it so happens that most of the times we parallelize the loops because those are the most time consuming ones, but you should be able to even parallelize, let's say even if there is a function call, you should be able to parallelize that function call with different values of I and so on. In case of Fortran, you will use a slightly different syntax, but essentially the clauses remain the same. The second construct that we are going to study is about the kernels clause, which I was mentioning, that you just put some piece of code inside kernels and depend totally on the compiler to figure out which ones to execute sequentially, which ones to execute in parallel, what should be the kernel launch configuration, that is with how many threads it should run, etc. All of this is taken care of by the compiler, which can be very useful initially, or in parts which are not really accessible to you. For example, in companies, when you are parallelizing some code, in case that is the job that comes to you, if you are not, I mean, there will be some code which is written by somebody else, and you are not able to see how, even understand that code, right? So you might be able to even give that to the kernel's pragma and let the compiler do its magic, right? So that could be one good initial way of checking if you get the same answer, as well as get at least some parallelization out of that without even understanding what that code does. Okay, and the last one, which is, I mean, nonetheless required, is the ACC serial, which executes your code serially. One would imagine, why would you require that? I mean, if you don't specify any pragma, then anyway it is going to run sequentially. Yes, that is correct, but there will be cases where you are actually inside a parallel construct, but you don't want certain part to be executed in parallel. So at that time you can specify serial, and then that code will execute in a sequential manner. But remember that this serial is not the same exactly as without the pragma. The reason being that this serial means that this is running serially on the accelerator. If you don't specify anything, then it will be running sequentially on the host or the CPU. Okay, so that difference definitely comes into picture when we are talking about serial. Okay, so although I mean, as I was mentioning, this compiler is written actually quite well, and although we usually parallelize for loops, just to convey to you that the compiler has a lot of flexibility, I'm just going to give you another example where instead of that for I equal to 0 to 99, I'm going to run it using a while loop instead of a for loop. And I specify the same pragma, hash pragma ACC parallel loop, and I use a while loop and I perform exactly the same processing as the for loop. And still the compiler will be able to figure out that this code, how this code needs to be parallelized, and it will execute it in a similar parallel manner on the GPU. Right? So that should allow you that even if you are specifying hash pragma ACC kernels and allowing the compiler to figure out, it's not that only for loops will be parallelized, but even your while loops can get parallelized, which can actually sometimes be helpful. Sometimes it may not be. Sometimes you don't want while loops to be parallelized. In such cases, that serial clause is going to be helpful for you. Okay. Any questions so far? All right. So yeah. So one another part that I should mention when you are trying to compile your code for the first time on your GPU is that sometimes you might have to specify additional arguments over what I am specifying in the slides. Usually with most of your Linux installations and NVIDIA GPUs, this pgcc-ac hello.c should work. But in case it doesn't, depending upon the GPU you have, depending upon the NVIDIA compiler that you have installed, depending upon the NVIDIA driver that you may have, you might have to specify some additional parameters like -ta equal to Tesla, cc70 and so on, just to make sure that just try out these arguments also in case your code is not initially giving you this parallel output, right? Maybe it is giving 0 to 99 or 0 to 999. Try running it for larger number of threads just to make sure that you, I mean, learning all of these OpenACC constructs is important, but you should also be able to make sure that it is actually running in parallel on the GPU. Right? Okay, so with that, we kind of come to the close of whatever I wanted to convey in today's portion. So we looked at some of the OpenACC basics. We looked at the Hello World program, and I mentioned a few things related to the installation and the output that the PG accelerator information binary is going to give you. Those of you who are aware of CUDA programming, you will see some similarity with the device query output that you get by installing CUDA and running this device query executable from the CUDA SDK. So essentially, we want to get the device properties. After that, we looked at some of the high-level aspects related to different commands which are available. Then I also briefly told about different types of parallelism that exist, the overall OpenACC execution model, the host side of it, and the device side of it. We briefly talked about the 3 levels of parallelism: gang level, which is coarse grain, then the worker level, which is the fine grain, and the vector level, which is the SIMD execution. But we also said that the vector lane is the one which is essentially referring to the thread. We looked at the overall GPU hierarchy. We briefly discussed about the command queues, which are similar to the streams on the GPU. And finally, I mentioned to you that the compiler is intelligent enough to execute even your while loops, and we should be able to get into the parallel constructs tomorrow. So yeah, that is all from my side today. We have around 13 minutes or so for the question answers. So I'll stop here. If there are any questions, we can take those up now. So as I have mentioned a couple of homework exercises. One is to check the rank of Param Siddhi. The other one is try out these codes. Right? So I would like you to try out this Hello World program. Make sure that it is running in parallel. I think, as they say, programming cannot be learned in class. Right? Of course, these lectures will give you enough examples from the slides, etc. So I'm going to tell you both from the theory side as well as the practical side. But until you try it out, it's going to be difficult. Like they say that swimming cannot be learned by reading a book, right? And the same is true about programming, and more so about parallel programming. So I recommend everybody to install OpenACC compiler, PGCC or PG Fortran, and try out these codes. There are all these codes I have made available from the Google Slides, the Google Sheet. So please try out at least some of those so that you get familiar with the setup and are able to run these codes. Right. So if there are any questions, feel free to ask. Okay. Himanshu is saying, could you recommend any cloud platform to try out these codes? I think these work with Google Colab, but you might have to install the PGI compiler via the commands that are mentioned on the website. So Google Colab should be able to run your codes. Yeah, I haven't tried it out, but I'm sure there are people who have tried it out. So some of their Python notebooks should be available, which you can import and try executing those commands. So that should be okay. Sure. Yeah, in case some of you do not have a GPU installed, or your institute does not have a GPU, you can try Google Colab. In case one of you becomes successful, feel free to share that information on the group so that others can also try it. Yeah, some of the installation instructions I have posted on the as one link. So one of our students from PhD Tech who is working with us, Venkata Krishna, he has given those commands. So please try it out on your laptops. It should be fine. And if there is any trouble, just post these queries on the Google. All right. So I don't see any further questions. So we'll stop here. A little early today, and we'll meet tomorrow.